Excuse me, teacher.
Yes, please.
When you are finding the approximate value,
Yes.
do you only find it by rounding off?
That's a good question. Now here they didn't tell us what we're doing here. Now here they would be maybe by rounding off the stated accuracy. I think something like that. You don't find it by only, it depends on what the question wants. They may say by rounding off or by truncating. So here that hasn't been captured. And I think that's a very good observation. So find the relative error in rounding off the following to the stated accuracy. I think that would be more precise in rounding off. That makes more sense. Rounding off the following the stated accuracy. That's now makes sense. So that we find the approximate value by rounding off. Somebody can find the approximate value by truncating, something like that. So you can find the approximate value by truncating or by rounding off. And in this case, we've been clear, we're saying rounding off. And I think you can now handle the rest. You can do the rest. Let's go to the next one. Relative error. How do we find relative error? I'm repeating this. This has been worked on already, I think. Remove that. The next term that we're going to look at is, I left out percentage error. I think it's supposed to be here. Let me insert there, percentage error. There should be percentage error somewhere. I don't know how I left it out. Percentage error, it is here. Okay, the other term that we need to look at is percentage error. How do you find percentage error? We're simply saying if you write the relative error as a percentage, expressing relative error as a percentage, what you come up with is what we refer to as percentage error. So in simple terms, for you to find percentage error, you get, where is it? For you to find percentage error, you get relative error, and you get relative error and you multiply by 100%. Or you get absolute error divided by exact value, or absolute error divided by the approximate value, then multiply by 100%. And that will give you the percentage error. Those are the basic terms that you need to know in error analysis. If you know them, then everything will be very okay. If you don't know them, then error analysis will always keep disturbing. You need to know how to find the error, what an error is. It's simply a deviation from the exact value. Then next, you need to know what an absolute error is. When you take the magnitude of that error, you come up with what you call the absolute error. Then the other one is relative error. How do you find relative error? If I've been given the exact value, I'll get relative error by dividing absolute error divided by the exact value to give me the relative error. Or absolute error divided by the approximated value, it will give me relative error. I've just shown you that in the previous example here. You notice that the two give us a negligible difference. The difference between them is negligible. It is ignorable, something like that. So for percentage error, you again carry forward. After finding your relative error, simply multiply it by 100 and end up with percentage error. Since you're dealing with errors, only round off if you've been asked to round off. Otherwise, write everything you see on the calculator for the accuracy, because we're trying to minimize errors by accounting for errors. You can't again create another error by rounding off your answers. So in most cases, write your answer the way you see it. Maybe if they say they have specified the accuracy that you should write your answer to, that's when you end up rounding off. So percentage error is here. They're saying this is relative error expressed as percentage. That means you get absolute error divided by the exact value or approximated value times 100%. Somebody has a hand up. Yes, John? John, your hand is up.
So what if you give your answers of fraction?
Answers of fractions?
Yes.
Yeah, you can use it right as a fraction or as a decimal, no problem.
Okay, sir.
Yeah. Okay.
Sir,
Yes, please.
sir, do you mind doing one more?
One more on
Yes, sir.
relative error.
On, sir, both absolute and relative.
Sorry?
Sir, both absolute and relative.
Okay. Let's come here and do one more. Let's do this one of 333. They're asking it find. This one's not moving along with the work. That's where the problems are coming from now. Okay, so we have this. We want to find the absolute error in that. In rounding off, in approximating this, the stated accuracy, we're writing this to 4 dps. So we shall have, in fact, let me write rounding off to be more specific. Rounding off. So here we shall have my exact value. What's my exact value? The exact value, which is x, exact value, which is my capital X, is the same as 0. How many threes are these? There are 5. 1, 2, 3, 4, 5. That's my exact value. What is my approximate value? Approximate value, which is small x. We're rounding it to 4 dps. This will be 0.1234, something like that. What is my error? So the error is obtained from the error, which we're calling this, you can use that symbol, will be the same as the exact value minus the approximated value. Exact value minus the approximate value. So here we shall end up with 0.33333. That's my exact value. Minus what's the approximated value? 0.333. 3 again, because we're writing 4 dps. This gives me the error as 0.00003, like that. It is positive this time round. The other time it was negative. So my error, absolute error, will be the same as the magnitude of 0.00003, like that. But magnitude of a positive value still remains positive. So this gives me 0.1234. That's my absolute error. Is that okay now?
Yes, sir.
Okay. So when you go ahead and find the relative error, now this has been intermingled because I shifted some few things. Okay, let me try to delete a few things here. Okay, so let's go to relative error. Here we had, I can even repeat this same one. I'm sure you can understand still. So this one we said to find, of course we have the absolute error in this already. Our absolute error in this, which is the absolute error, we got it as 0.00, if you can remember it, 00, another 0.33, like that. That's our absolute error. Now I want to find relative error. Relative error will be the same as absolute error divided by the exact value, or we can say absolute error divided by the approximate value. So this will be the same as, if I can get more space here, our relative error will be equivalent to, what's my absolute error? 0.00033 divided by the exact value, which is 2.24567. And somebody gave us this answer as what? 0.000. What was the answer? I can't recall.
146.
1469449.
9.
Then we said, or you can say relative error is the same as the absolute error, 0.00033 divided by the approximate value, which approximate value will be, in this case after rounding off, to be 2.246, and this still gave us 0.000146927. So we said, yes, we used approximate value. Here we've used, in this case, we've used, let me pick this. In this case, we've used, this is unapproximated, this is the exact value, and this is the approximated value. But we're seeing that the first, almost the first, how many digits, I don't know, these ones are the same. The difference is only in the last 2 digits, which is not a big difference. Because in most cases, they'll even ask you to round off to state this answer to a given number of DPs. So you notice that these two even will be ignored. Even if I decided to round off here, if I round off, this 4 will be ignored. And even if I round off here, this 2 will be ignored. If I round off from here, this will be 5. This will be 5, and this one will be, will come to 3, which difference is very small. So that's what we need to know there. Somebody's in the chat. Let me see what this one has to say. Okay, chat. I'm saying, can you write the answer in standard form? That's what somebody's saying. Is it possible to write the answer in standard form? The challenge with standard form is you may end up ignoring some digits and you create some errors. But if you capture all the digits in standard form, then it is also fine. For instance, here, I can say the error is 1.46949. I capture all the digits, then times 10 power 1, 2, 3, 4, 5, 6, 7, 8, 9. Power -9, something like that. Here it is also okay. Since you've captured all the digits, there's no error created by you writing it in standard form. But if you write in standard form and you end up writing 1.47 times 10, here you'll have created another big error. So what you should avoid here is, since we're dealing with error analysis, avoid creating unnecessary errors. And you can create, we looked at rounding errors. As you're rounding off, you're creating an error. So to avoid that, don't round off anyhow, unless in the question they've asked you to round off. The person who asked us to repeat, is that okay? Should we proceed now? Or we try out one more again on relative error? I'm waiting for a response. Yes? Should we do one more or we proceed? Hello?
One more.
One more. Okay, let's do one more. We can do 2 more, even 5 more, till we get the concept. So the other one here, we want to find relative error in this, relative error in that. We shall say, of course, you know the formula for relative error. These are the things you must get at the back of your mind. And the other challenge is error analysis. We don't have quite a number of reference books on error analysis. I mean, in numerical methods generally. You must have noticed that there are very few books that you can get with error analysis, and most of them are pamphlets. So that means we don't have a lot of reference material for it. Okay, so we say relative error is the same as absolute error. When you see the error inside and there is this sign outside, we're dealing with absolute error, which means positive only. Divided by the exact value, or we can say is divided by the approximate value. In this sense, we're saying capital X is representing the exact value and small x is representing the approximated value. Now, since we've done it already in part A, I'm not going to waste time in looking for the absolute error. I'll simply quote it. We have absolute error, we got it as 0.000, I think another 0.3, like that. That was our absolute error. Excuse me. So we have that. So relative error will be the same as 0.00003 divided by the exact value. Exact value is 0.00. Sorry, I'm used to getting addicted to writing zeros. Okay, that 0.33333, like that. What does give us? You compute using a calculator. That will give us I'm listening.
9.0000.
Sorry?
9.0000. 4 zeros.
Oh no. You've divided this by that. Do the computation correctly. Is 0.0003 divided by this. Or you're dividing 0.3 divided by that.
We get 0.0000.
How many zeros? How many zeros?
4 zeros before, after the point.
9.
Then 9.
Okay. That's exactly how you've rounded off. Hello?
The full thing is 0.000090009.
0009, like that. Okay.
Yeah, that's all of it.
What about when we use, here we're using the exact. Here we're using exact. Let's see here when we use approximate. Somebody wrote this on our screen. Can you try to delete it? Is somebody annotated it here? Delete it, please, so that because it's interrupting with our working space. So this will be the same as 0.12343 divided by, excuse me, the approximate value. This will be 0.3333. What does it give you? 0.12343. 1, 2, 3, 4, 9. Then I'm listening. Let's carry out this computation very fast to avoid the delay. Because this lesson is only 1 hour and 30 minutes, we use 1 hour already. We're left with 30 minutes.
Chat 3 zeros.
Sorry?
3 zeros, 0, 0, 0, and then 9.
Then
9.
Yeah. You see that the error is, the relative error is the same in this case. So that's why we say you can divide by the exact value or divide by the approximate value. Either way, you'll come up to the same thing or close to the same thing. Yeah. So while copying the notes, I'm going to share with you this. So make sure you some of you are playing with the screen, I don't know. You're playing around with the things. Okay, so somebody should delete this. The other thing is, when you keep interrupting, I get distracted. So this is what you're going to do. You'll continue and finish up these examples, these last examples. Now, at this point, you must have learned that finding absolute error is simply get the difference between exact and approximated value, then take the magnitude. We shall apply this in numerical methods, in the Newton-Raphson method, trapezium rule. We shall apply this everywhere in all the other areas of error analysis. In fact, error analysis is the backbone of numerical methods, because even in linear interpolation 2, we're going to look at linear interpolation 2, look at linear interpolation 1. Hope you've not forgotten it. In interpolation 2, we're going to still apply the same concept of error analysis, how to get the error. Trapezium rule, we shall also apply the concept of error analysis. Then iterative methods, flowcharts, all the other areas. There is no any other area in numerical method that you can talk about that has no error analysis. So that's why we should take an ample time to conceptualize it, so that we don't misfire when it comes. Somebody's in chat. This one saying, the orientation, please disable. Okay. Let me first work on this one. Okay, if you have a question, you may ask, well, let's see. Okay, you can now delete it. Then I've opened the screen. The person who wrote this can now remove it. Remove, then you proceed. Okay, percentage error. We're saying percentage error. If you've understood how to find relative error, then percentage error is just a walkover. Percentage error is just a walkover. You will simply let's do it here. You'll simply multiply relative error times 100. Now, like this one here, if you want to find percentage error in this, you simply multiply this by 100%. Multiply relative error by 100% and will give you percentage error. As simple as that. I want to get relative error in this, percentage error in this, multiply relative error times 100% to give us the answer. Let's just do one here. I'm sure this is not something that we should spend decades on, but I'm going to give you another example that's a bit more detailed. So here, percentage error, as the formula states, you simply get percentage error. Percentage error will be the same as relative error times 100%. So this will be the same as relative error times 100%. This will be the same as what did we get as the relative error in this? It was 0.000. Were they 3 zeros, 4 zeros? I can't recall. 3 zeros. 1, 4, 6, 9. Somebody's in chat again. Let me. I have to keep checking the chat. If you have something, please, that you think you can't ask directly, just go to the chat and type it there. I'll see them. I'll receive a message here. I'll check it out. Unfortunately, this one is also not easy to find. Okay, it is here. It says I need to delete notation, but can you write confirm? Yeah, so we have, this is our relative error. I simply multiply this by, what were the other digits? I think 49, something like that. I multiply this by 100%, and my relative error, this one should focus, we just remove. Please stay in a environment that noise is nagging, no? Make sure in a quiet environment to avoid that noise. So we have this. So remove the first these two zeros, and we shall have 0.0146949%. That means that by you writing, please mute yourself. Or stay in a quiet environment if you can't mute yourself. Be in a quiet environment so that you don't interrupt us. Okay, so we're saying relative error times 100% gives us percentage error. So relative percentage error is simply relative error expressed as percentage. And there's something I wanted to say, but no one people keep interrupting. You lose focus. Now here we have our percentage error as that. When I recall it later, we shall talk about it. But that's how we find percentage error. By you approximating 2.24567 by 2.246, you create an error of this percentage. The percentage error will be this one here. And that's why you find on some labels, you know, it is very hard to deal with very accurate values. It is, in fact, practically impossible to have very, very accurate values. So it's normal for us to make errors somewhere, but these errors must be within the required limit, the tolerance. We're going to look at the tolerance in the next term. The next term below there is about tolerance. So these are the terms that we're going to meet in error analysis. Here, because we're learning, of course, we looked at them in order. We've had the error, then gone to absolute error, then gone to relative error, then gone to percentage error. But in exams, it may not be the case. They may give you percentage error and ask you to find absolute error. They may give you relative error and they can give you anything and ask for anything. So you must know those transitions. How do you get what from what? How do I get absolute error from percentage error? How do I get relative error from absolute error? If I know how to get relative error from absolute error, then I should also know how to find absolute error from relative error. It is two-way. So don't just cram it unidirectionally. It is not in one direction. It can also be asked in the reverse direction. So I think that's something you should know. Let me get you a question. This one you can do it by you rounding off. Let me change this one also to rounding off, because you can approximate by truncating. You can approximate by truncating. So let me use rounding off. So if you round off this, you're going to create an error of 0.0146949%. If they give you absolute error and ask you to find relative error, you know how to do that. Now, if they give you relative error and ask you to find absolute error, what do you do? Of course, you play around with the equations. Let me get one simple question from, I have questions down this way. Did I copy them here? I did not. Let me just copy it from this side and bring it here. Somebody has a question? Okay. Okay, so let me copy this. I paste it there and then there is one good question here. We're going to look at all these questions, but there's one I'm interested in here. Let me see, a student measured the length of this and that. The question is not coming. Where did I see it? You look at that number 4. Number 4, they are saying a value of P is this, was obtained in a certain experiment. Given that the relative error in the measurement of this value is 0.01%, now that is percentage error because I've given you relative error in percentage form. So that is percentage error. Find the limits now. We shall look at the issue of the limits later, but I simply wanted to show you that there are some questions where they can bring when they have given you percentage error, but they want you to find what? They want you to find absolute error. So we're going to look at such questions later. I may not bring it here now because this is higher order and yet we're just building our concepts. So I don't want us to bring in those higher order concepts at this point. So you'll continue and do the remaining parts. Is there anybody with a question on this? Hello? Hello?
Hello?
Hey, do you have any question on this?
No, sir.
You've known how to find percentage error, isn't it?
Yes.
Okay. Now, the next area we're going to deal with, we're now diving into the details of error analysis. We're building it slowly. Make sure you get these things. You allow me. Let me just attend to this shortly. Yes, hello? Yes, please. Morning. I'll be there in 10 minutes. I'm not there. You can enter inside into the house. Yeah, sorry for that, but it was some important call I couldn't miss. Okay, so we have this. You have learned how to find percentage error. Let's now go to this term here, maximum absolute error. Now we said you can find absolute error by simply getting the exact value. Then after getting the exact value, you subtract the approximated value. Then after that, you take the magnitude. That gives you the absolute error. But in most of the questions you're going to find, maybe apart from trapezium rule and maybe Newton-Raphson, most of the questions you're going to find, you will not have the two of them. You'll always have one. You'll either have approximate value only, or you'll have the exact value only. Now, if I have one of them, how do I find the error in that value? They always give you measured values. They can say a value was measured using a ruler, or the value was measured using a voltmeter, or the value was measured using. So they'll give you measured values. How do we determine the maximum absolute error or the maximum possible absolute error in that measured value? That's what we're going to look at. Or they will say this value has been rounded off to the given number of decimal places. Find the maximum absolute error in that value. So you have to be attentive here. How do you find that error? Let me show you something here. I'm going to demonstrate something for you here. Let me give you this. If I have, let's be attentive here. When I have a value like, let's say 2.2, and I round off this to one decimal place, I'm going to have 2. What have I done in between here? I've ignored 0.2 to come up with that. If I have a value, let's say 2.6, and I round off this, I'm going to have 3. What have I done here? I've added 0.4. So that means that this value here, I don't like such, you know. So I'm trying to build a concept, somebody's making noise. So we have 2.2, and I have written it as 2. So that means that this 2 has an error of 0.2. There is a negative error. I've subtracted 0.2, something like that. So here I have 2.6, I've written 3. There is an error here of 0.4. If I have 2.5 and I write it as 3, round it to 3, round it over to 3, I'll have made an error of 0.5 because I've added 0.5. If I have 2.9 and I write it as 3, round it off to 3, I'll have made an error of 0.1. If I have 2.26 and I write this one as 2.3, I'll have made an error of 0.04. Now, how do I, that means that as you round off, you've not seen anywhere where we're adding 0.06. You've not seen anywhere where we're adding 0.07 or 0.08. If I have 2.24, and I write this as 2.2, I'll have ignored 0.04. So that means that all errors that we're going to make in this case, the errors we're going to make will end in a 5. The errors you make by rounding off will end in a 5. So if you find any value that has been rounded off, then the maximum possible error that can be in that value has to end in a 5. For instance, if I can just look at a value. If I see 2.26 and they say this value is rounded off, if I see 2.26 and they say this value is rounded off, then either this value was 2.261 and they rounded off to that, or it was 2.262 and they rounded off to that, or it was 2.263 or 2.264 or 2.265 or something like that. Or it was 2.259 or 2.258 or 2.257 or 2.256 or 2.255, but no less than that. So you see that here the error made, if it was 2.25, if it was like this, and wrote that 2.26, that means that here we added 0.005 to come up with 2.26. If it was this, then we added 0.04. This is 0.003. This is 0.002. 0.001. This one we removed 0.001, 0.002, 0.003, 0.004, 0.005. So you notice that the maximum possible error, that I make in writing 2.26, in rounding off any value 2.26, the maximum possible error that could be made in this is 0.005 or 0.005, like that. The maximum possible error that could be made in rounding off this to that. Because here they have given us the approximated value, but they have not given us the exact value. So we are trying to find out what could be the error in this value. We can't tell because we don't have the exact value. So we can't get that difference of exact value minus the approximate value. But we're simply getting, if there's an error in this, what could be that maximum possible error? What we call now the tolerance. We're calling it the tolerance. Maximum possible error in a given value is what we call the tolerance. Just like you can say, maybe for you to make a standard cake, you need maybe a kilo of sugar. But of course, as you're measuring, if you don't have the tools for measuring, you make some errors. If I put 1 kilo and a quarter, maybe the cake did not affect the cake so much. Or if I put a half and a quarter in it, it may not affect so much. But when I just put 2 kilos, it will affect the taste of the cake. It has gone beyond the maximum tolerance. You know, you've made an error, but you've gone beyond the tolerated error. You see that? Or if you put a half, somebody will eat and I think this one not done in half sugar, something like that. You've gone below the tolerance. So they'll give you an approximated value, and you're supposed to find the error in it. But you've learned that for you to find the error, you must get the exact value minus the approximate value. But in this case, you don't have the exact value. How do you find the maximum possible error in that value? How do you find the maximum possible error in that value? We're saying, just like we've seen here, the maximum possible error in 2.26. In 2.26 is 0.005. How can we arrive at this? Do we have any formula that can help us arrive at this? We are saying that if you want to find the maximum possible error in any value, any approximated value that has been rounded off to a given number of decimal places, the formula is this one here. This is the general formula for finding. This is the formula we're going to use. Maximum absolute error in any value, in any number that has been rounded off to the given number of decimal places is obtained from this, a half times 10 to the power negative n. What is n? What does n represent? Let me give you what n represents. You need to know this because this is now what we're going to look at most here. Let me create space. Yes. What is it? Where n represents the number of decimal places. That's what n represents. N stands for the number of decimal places. So they'll give you an approximated value. Now here, in the first examples we had of rounding off, round off this one, we rounded off to that. Round off this one, we rounded off to that. If you try to get these errors, the difference between the rounded off value and the exact value, you'll notice that that value lies between 0 and 0, maybe 0.005 or 0.5, or it never goes beyond. You can never find 0.6 as the difference. So our maximum possible error, maximum absolute error should end in a 5. And how do you get it? Get like this. So if they give me a value, they can say A was obtained, A equals to 2.36. It has been rounded off. They will tell you that it has been rounded off, so that they give you a hint on how to find the error. It was rounded off. How do you find the error in this? Find the error in writing A to this number of decimal places. So here you say the error in A will be the same as a half times 10 to the power negative. How many dPs are they? Negative 2. That's how we find the error in this value. You see that? That's how you find the error in this value, and therefore this will be the same as 0.005 You notice that's the same, almost the same as what we were doing here. This was 2.26 and we found the error as 0.05. That's the maximum possible error that can be made in that value. That is if they have not given the exact value. If they have given the exact value, obviously you get the exact value minus the approximated value. It will give you the error. It will give you that exact error. But now here we're just getting the range within which the error lies. We're getting the range within which the error lies. So now let me go back to this simple illustration that I gave you here. We said 2.26. This 2.26. They have written it to 2 dps. What is the maximum possible error that they made? That this person could have made by writing this? We don't know the exact value is. The exact value could have been 2.21, could have been 2.22, 2.2. I mean 2.6, 2.261, 2.62, 2.63, like that. We don't know. We're just speculating, So you notice that our speculation ends on this and that one. So that means that this value, the exact value of 2.26, because it's approximated value, the exact value of 2.26 lies between 2.265 and 2.255. This is what we call the lower limit of the exact value, and this is the upper limit of the exact value. No, are we together? Or I've used very many words and some of you are lost. Can I have some responses before we proceed?
Teacher, the upper limit 2.264. 2.264.
2.264.
Yes.
Yeah, why? Because if you take over the 5, it takes it to 2.27, isn't it? Okay, that's a good observation also. We shall look at this in detail later. So the upper limit is 2.264. The lower limit is 2.255. So they can ask you, find the limits within which they can give you a value like 2.36, and they say, find the limits within which the exact value of this 2.26 lies. They say A is 2.36, it has been rounded off the given number of decimal places. Then they say, find the error that this person made. That is part of the question. Part B, they will say, find the limits within which the exact value lies. So how do you find those limits? I simply get this value plus the error. That gives me the upper limit. That's what we do. This value plus the error gives me the upper limit. This value minus the error gives me the lower limit. We're going to look at such things in details. Okay, that's what we have here. Then the other approach is, they may ask you to find maximum absolute error in a value, like this one, 2.36. We've seen how we find it. It is a half times 10 power negative n, where n is the number of decimal places. Now, what if they just give you the maximum value and they give you the minimum value? They say somebody measured and his maximum was supposed to lie between this and this. They give you the maximum and they give you the minimum. Then they ask you to find, the absolute error, the maximum absolute error in that person's value. Let me create more space here. Now, if I have my maximum value, if my maximum value is, let's say my maximum value is 2.265. It has been given as that. My minimum is 2.255, and they ask you to find the maximum absolute error in the value. Of course, they are saying the exact value lies between maximum, this one, minimum, that one. Then they ask you to find the error, this person, the maximum possible error that this person could have made. This will be the same as 2.265 minus 2.255, like that. Divide by 2. Maximum value minus minimum value divided by 2. So this will give us, if you subtract this, I don't know, what do you get? 0.01, I think, because this 5 goes away with that. This 6 gives us 1, this must go away. So this gives us 0.005. We're going to look at this in details next time. How do you find the error bound, the maximum absolute error in a given value or function? We shall look at function later on. Or function, when you have the maximum value and you have the minimum value. In this case, you simply get the maximum value minus the minimum value divided by 2. This should not be crammed. I can give you a simple illustration here. This is what we're dealing with. We have something like this. Our exact value is in between here. We don't know exactly what it is. But we have the minimum value, maximum value this way, and we have the minimum value here. So if my exact is here, how do I get the maximum value? Of course, when I add the maximum possible error. If I add the maximum possible error, I'll get the maximum value. If I subtract the maximum possible error, it takes me the minimum value. So we're saying you can get this error by getting the maximum value, you subtract the minimum value and divide by 2. That will give you the error. Of course, when I get this minus this will give me 2a. When I divide by, 2e. When I divide by 2, it gives me the error. Or I can say maximum value minus the exact value. It will still give me the error. We can add here another option. Or maximum value minus the exact value. Or the working value. We shall call it the working value sometimes. Working value. That will give me the error. Or I can say exact value minus the minimum value. Either way, this will give me the error. So in the interest of time, I want to, because you have other classes, this being introduction, we cannot do too much. But I think at this point, you understand the basics of error analysis. You know how to find the error. We say the error, you get it by subtracting the approximate value from the exact value. That is the error. Then absolute error, we say we subtract and get the magnitude. That gives you the absolute error. Then we said relative error, you divide absolute error by the exact value or approximate value to give you relative error. Then we went to percentage error. We said percentage error is relative error times 100%. That gives you percentage error. Those are the major 3 terms that you should understand in error analysis. They can give you any of them and ask you to find the other. They can give you, of course, while learning, we started from up, error, absolute, relative, percentage. But while asking a question, they can give you percentage and ask you to work it the other way around. So you need to, you need less cram it, but you need to understand how each one comes about. So I'll just stop there for today. It is already 10:34. Maybe if you have questions, you have suggestions, you have some compliments, something like that, you can bring them forth. Somebody says it had failed. What is that? It has failed, sir. What has failed? Can somebody tell us what has failed? Someone say, teacher, when finding relative error, the calculator gives in standard form, and when you change to normal, it truncates it. How do you go about it? Hey, somebody says, yeah, when you find you're using a calculator, some of the calculators give you in standard form, and when you go to normal, it truncates it. Now, in that standard form, you can tell. You write it in standard form, but even in standard form, you can now tell how many keys you're supposed to write. If the calculator gives you maybe 1.2 exponent -3, you can just know that that is 0.00012, something like that. So try to practice your that standard form things. and you get it. So next time we shall dive into the details, we shall look at the limits of accuracy. How do you find the limits? I've just talked about them here shortly. How do you find the limits? Sometimes we call them limits. We shall look at the difference between when they ask for limits, range, or interval. How do you deal with those three terms? Then from there, we go to some villages here annotating on my screen. Okay. So we shall look at limits, limits of accuracy. How do you do that? We look at the maximum absolute error in addition, when you're dealing with addition, when you're dealing with subtraction, when you're dealing with multiplication, when you're dealing with division. That will mark the end of the first section of error analysis. Then we dive into the other one of deriving the formulae. Then afterwards, we look at errors in differentiable functions. So I'll request Ms. Opie, I think we'll meet you soon, and we'll be teaching you differentiation. We need that differentiation here because at a later stage, we shall be applying some bit of mild differentiation here. Then also you need some bit of trig. Trig we shall apply basically double angle somewhere at a later stage, but you won't be very serious. Just in case they don't teach you there, I'll try to give you a hint here and we proceed. So my endeavor is to enable you cover a lot of, let me stop screen share. My endeavor is to make sure I even stop recording since